Okay, we're going to look at transformations. Transformation of a plane takes a point A in the plane and maps it onto one and only one image, A dash, lying in the plane. So you've got your object point. Your original A point is xy, written as a column vector, and the image is x dash, y dash, also written as a column vector. Transformation is said to be linear if any linear relationship between the position vectors is conserved under a transformation. So for example here, you've got mu times position vector p plus alpha times position vector q gives you position vector A. That's the original object thing, I suppose. And then if you transform this such that p becomes p dash, q becomes q dash, then the relationship is still conserved. So A dash is equal to mu p dash plus alpha q dash. Also, all linear transformations can be expressed as a pair of equations of the form x dash equals ax plus by, y dash equals cx plus dy. So that's your new x, your new y, that's your old x or your original x and your original y. This is more commonly written this way, where you've got as the matrix form x dash y dash is equal to abcd upon xy. Okay, a couple more things about this. The transformation matrix can be found by finding the image of 1, 0 and 0, 1. So if you want to find what matrix represents a certain transformation, all you have to do is see what happens when you transform 1, 0 and 0, 1. So for example, if you were reflecting on the y-axis, you would see where 1, 0 goes to, see where 0, 1 goes to when you reflect on the y-axis. And then those two new column vectors, push them together and that becomes your final result. The reason why this is, if you look here at some general matrix A, B, C, D and you multiply it by 1, 0, what you get is the first column of your matrix. You look again at your A, B, C, D matrix and you multiply 0, 1, what you get is the second column of the matrix. So the image of 1, 0 is the first column of the transformation matrix, and the image of 0, 1 is the second column of the transformation matrix. Another key point is under any linear transformation, the origin 0, 0 maps to itself. So that means under a translation by a vector rs, the transformation equations are x dash equals x plus r, y dash equals y plus s. So if you imagine you put 0, 0 into this, 0 will now become 0 plus r, so r, and put in the 0 for the y, and your new y will become 0 plus s, so will become s. So 0, 0 has not been transformed to the origin again. It has not happened. Therefore, a translation is not a linear transformation. Okay, if you're asked to find a transformation represented by a matrix, the easy way to do it is to find the image of the unit square under the matrix. So just on a wee sketch here for what the unit square is. So you can imagine that is your origin. That would be 1 and that would be 1 as well. So that is 0, 0, that is 1, 0, that would be 1, 1, and that would be 0, 1. So you transform all of those points. So here you can see I've just said give the geometrical description of the effect of the matrix 1, 0, 2, 1. So we're doing 1, 0, 2, 1 to all those 4 points. There they are in column vector form. And I've done that out for you and you can see that's what you get. You can do that for yourself just to prove it. And if we do the sketch of this, you can see here you've got your 0, A, B and C. They were your original things. 0 and C have remained the same, where A dash and B dash are the same as A and B, but they've just been stretched up. This is what is known as a shear. So in this one, this is a shear. You need to state what's called the invariant line. So the invariant line in this case is a y-axis. The invariant line is a line which stays fixed. You also have to state one point that you know moves. So it can't be on your invariant line. So I've just used A. Okay, so to sum that up, shear, you must state the invariant line. So that's a line that doesn't move. And the image is some point not on the invariant line. Okay, we'll move on to this example. It says find the matrix corresponding to each of the following linear transformations. So I've filled in a wee bit of this for us already. First one is rotation of 90 degrees anti-clockwise about the origin. So remember earlier on we said what you had to do was find out where this point moved to. So 1, 0, and also where this point moved to, 0, 1. So this will give you the first column of the matrix, and this will give you the second column of the matrix. So I've done out the sketch of the unit square, and if we rotate that 90 degrees anti-clockwise, so a quarter turn anti-clockwise, the point 1, 0 will actually be rotated up to here. So 1, 0 becomes 0, 1. Also, 0, 1 is going to be rotated. I'll just fill in the rest of this thing for us, the rest of this square. So this is the image. So it's going to 0, 1 I should say, is going to be rotated down to here, and that's going to be minus 1. It's going to be minus 1, 0. So we can now fill in, this is going to be a first column for matrix, this is going to be a second column. So we just fill that in here. That's going to be 0 and 1, and then minus 1 and 0. You could prove that to yourself if you wanted. What you could do is take this matrix and multiply the 2 by 4 matrix, the 0, 0, 1, 0, 0, 1, 1, 1, and so on, and you'd see that all 4 points that they move here. But there's no need to do that. Okay, this was a reflection in the x-axis. So again, we'll just do it out here. So if you have, there's your original unit square. If you reflect that in the x-axis, it's going to go down to here. So 1, 0 is on your mirror line, so it actually stays fixed. Whereas 0, 1 is here, and it's going to go down to 0, minus 1. So we can now fill in our transformation matrix. It's going to be 1, 0 is your first column, and 0 and minus 1 is your second column. Okay, in this example, what we've got to do, it says a linear transformation T has a matrix 2, minus 1, 1, and 1. It says find the image of the point 2, 3 under T. That means you find out what happens, where does 2, 3 go after you've multiplied it by T. So here I've set this out for us already with 2 minus 1, 1, 1 upon 2, 3. And if you just multiply it out, first row, first column. So let's just multiply your first row by the first column. 2 times 2 is 4, minus 1 times 3 is minus 3, 4 minus 3, that's just 1. And this is second row, first column, so that's second row times your first column, which is just going to be 1 times 2 and 1 times 3. Add those together, you're going to get 5. So notice how they gave the question, it was just a normal coordinate, so we'll give our answer as a normal coordinate as well, it was 1, 5. Okay, second example says the coordinate of the point having an image of 7, 2 under T. So we've got to find what coordinate do you start with such that the result is 7, 2. So this really is equation. We do 2 times minus 1, 1, 1 upon xy, and that gives you 7, 2. So what I'm going to do in this case, I'm going to let A be equal to the matrix, and first thing I'm going to do is find the inverse of A. So the inverse of A, the determinant first of all is 2 times 1 minus 1 times 1, so which is going to be 3. So 1 over the determinant. Go back and look over your inverse of a 2 by 2 notes if you need to. And I've just swapped the elements in the leading diagonal. And I've changed the sign of the other element. So that's my inverse of A. I'm just going to call that equation 1. And I will rewrite that equation just to make life a bit easier. That's A times xy is equal to 7, 2. That means A times A to the minus 1 times xy is equal to A to the minus 1 times the 7, 2. So we can A times A to the minus 1 is just going to be I, so that can just disappear. That's just be xy is equal to, and then we'll just write that in as normal. That's going to be 1, 1 minus 1, 2 times 7, 2. And if we do that out and see what we get, I'm running out of space here. That's going to be a third times a column vector then. First row, first column, so that's going to just be 9. And then that's going to be 7. That's going to be minus 7, and then plus the 2 is going to be, where are we? Minus 7 plus 4 is going to be minus 3. And then if you do that out, you're going to get 3 minus 1 And again, I'll just say my answer. I'll write it as a normal coordinate 3 minus 1. Okay, the other way you can do this question as part B is by looking at this as just normal simultaneous equations. So go back from the matrix form of the equation, put that back into simultaneous equations. So remember, that would be 2x minus y equals 7 and x plus y equals 2. So that's where we get these two equations. So I'll call this equation 1 and equation 2. So if we just add these two equations, we'll get rid of the y's. So you'll get 3x is equal to 9, which means x is just equal to 3. And then we'll just put that back into equation 1. 2 times the x is going to be 6 minus y is equal to 7. So that's going to be 6 minus 7 is equal to y. So y is equal to minus 1. So therefore your answer is just going to be equal to, what was it, 3 minus 1. So you can see I've got the same both methods. So whatever one you prefer. There are times I use this one, there's times I use this one. It doesn't really make a difference. It would just be if it specifies to say the matrix method, you would have to use this one. Okay, similar sort of example here. It says in this one, find the 2 by 2 matrix which will transform 1, 2 to 3, 3 and minus 1, 1 to minus 3, 3. So I've let my matrix, my 2 by 2 matrix be A, B, C, D. And notice 1, 2, so this column goes to 3, 3. Likewise, minus 1, 1 goes to minus 3, 3. I'm going to let my A be equal to this thing. I can't find the inverse of this. This is a algebraic term, so we can't really find the inverse of it as such, whereas we can find the inverse of this thing. So I'm going to find the inverse of A. First of all, your determinant of A would be 1 times 1 is 1, then minus 1 times, 1 times 1 is 1, and minus 2 times minus 1, so that's going to be 3, so that's 1/3. Change the elements in the leading diagonal, stay the same anyway, change the sign of the other elements, that's what you get. So my first equation, I've got A, B, C, D times my A equals 3 minus 3, 3, 3, that's what it was. So what I'm gonna have to do here to get rid of that A is I'm gonna have to put the inverse of A after it. So on the left hand side of the equation, the inverse of A is going after everything. So I've got to do the same thing here on the right hand side. So that inverse of A has to go over here. And the reason that's important, the reason I can't put my inverse of A over here, for example, is that the order of operations, the order of matrix multiplication matters. Of course, what we've got on the left hand side, A times the inverse of A, that just cancels out, gives your identity, so it effectively disappears. A, B, C, D, that's what you have. And then here we will do that out. My inverse of A was 1/3. Bring the third in front here just to make life a wee bit easier, to save us a wee bit of time. And then put the rest of the inverse of A here. What was it? 1, 1 minus 2, 1. So we'll just work down our page and see what we get. We keep this third. You could multiply. It's a nice one here. You could actually multiply in at this stage, but we'll not bother. And again, we'll have to do these first row, first column. So it's going to be 3 times 1, and then minus 3 times minus 2. That's going to give you 9. And then first row, second column, that's going to be 3 minus 3. That's going to be 0. Happy days. Next one's going to be 3 times 1, then minus 6. That's going to be minus 3. And then it's going to be 3 times 1 and 3 times 1. That's going to be 6. And then multiply that out. Multiply by the third, and you're going to get your 3, your 0, your minus 1, and your 2. So there you have your answer. Right, another way we could do this one is using simultaneous equations. So from here, from this original equation, we could go back to simultaneous equations. So we're going to look at the A and the B ones here. So the first row by the first column and the first row by the second column will get you these two things. So I'm going to have A plus 2B is equal to 3. So that was to get this element. I'll call that equation 1. And then my first row times my second column will give me A minus B, and that will give me minus 3. I'll call that equation 2. Now here, how are we going to get rid of these? We've got positive A. Oh, I've made a mistake there. That should mean minus A, and that should mean plus B. First row times my second column. So if we add here, we're going to get 3b is equal to 0. Happy days, that means b is equal to 0. Put that back in equation 1. A plus 0 is equal to 3. Okay, so the next thing we're going to do is find your C and your D. So we're using your second row, first column, and then to give you second row, first column will give you C plus 2D is equal to 3. I'll call that equation 3. And then your second row, second column will give you minus C plus D is equal to 3 as well, and that is your equation 4. So we'll solve these two equations. So again, we just add, and you're going to get 3D is equal to 6, therefore D is equal to 2. And then sub that into equation 3, you've got C plus 4 is equal to 3. So C is equal to 3 minus 4, C is equal to minus 1. Therefore, your matrix is equal to, my A was 3, my B was 0, and my C was minus 1, and my D was 2. So you can see two different ways. I've got the same two answers. Okay, last bit for us here. We've got our transformation matrix. So this is really about our determinant. So if a matrix T is transforms some shape ABC to its image A dash, B dash, C dash, then the inverse T to the minus 1 maps the thing back the other way. If the matrix T corresponds to a certain linear transformation, then the determinant of T gives a scale factor for any change of area under the transformation. So I'm going to use a very basic one here to show you this. So if you don't, well, ignore this one, I'll rub this out in a wee minute. But if you imagine 3003, now this is one we haven't talked about. I'm just going to multiply this with the unit square. So if you multiply this thing with our unit square, I'll just do the first 2 points, the first 2 important points, and that will do the job, and see what we get. If you do that out, what you get is 3003. So if you imagine what we have had, how I've got this, there was my unit square, and now what it's become is this thing which is 3 times bigger. So what the determinant of that thing is, if we look at this thing, the determinant of that would be equal to 3 times 3 minus 0 times 0. So the determinant would be equal to 9. And if that's a 3 by 3 square, its area is 9 units squared. And that's going to be 1 unit squared. Okay, so you can see the scale factor for area would be the determinant 9. Okay, I'll get rid of all that, and we'll get rid of all that, and then we'll look at this next example. Almost there for this bit. Okay, it says consider a transformation matrix 1, 2, 2, 4 and show that all the images lie on a straight line. Right, have not got a clue. So if you haven't got a clue, what you got to do is just put in a general point and see what happens. So I'm just going to multiply my general point xy by 1, 2, 2, 4 and see what happens. First row, first column is just going to be x plus 2y, and then second row, first column is going to be 2x plus 4y. So what we've shown is x dash is equal to x plus 2y. So the second row, if you do second row times the first column, you're going to get 2x plus 4y. So what we've shown is that your y dash is equal to 2 times your x dash. Therefore, we can say the image points lie on the line, and just get rid of the y dash, x dash, y equals 2x. Okay, the last couple of bits here. The first thing, it says if a matrix P transforms xy to x dash y dash, and a matrix Q transforms x x dash y dash to x double dash y double dash. That's just like the second way of second time of transforming it. Then the single matrix equivalent to p followed by q, which will take x y to x double dash y double dash directly, is given by qp. So here we've said x dash y dash is equal to p upon xy, and x double dash y double dash is equal to q upon x dash y dash. Therefore, if you go there directly, x double dash y double dash equals q upon p upon xy. So really it is qp times the original xy. So when you see this, like if I had written down a, b, c times xy, what you need to understand here, this means I'm doing c first, then b, and then a. So whatever's touching the thing is what you're doing first. So likewise here, that means qp really means you're doing p first, then followed by q. So that's very important that we understand that, otherwise we will not be able to understand the inverse. Okay, the next bit is about this inverse. It says if qp is the matrix representing the combination transformation xy to x dash y dash, then the inverse of qp equals the inverse of qp is equal to qp to the power of minus 1. So that means you have to reverse the q first and then reverse the p. So if you think back why that is, qp meant you did p first then q. So if you're reversing that process, you've got to reverse q and then you've got to reverse p. So that's really why that is. You can see the diagram here. Okay, to go from you have started with your xy, you did p to it to get to your x dash y dash, then you did q to it to get to x double dash y double dash, and we said in the previous one there, we said that was the same as qp. So to get back, you've got to do q first, inverse q first, sorry, and then you've got to inverse p, which is the same as inversing q first, inversing p. So the inverse of qp equals, and this is on the right hand side, so it means I'm doing the inversing q first and inversing p first. Okay folks, you're now ready to do the worksheet, the Matrices worksheet exercise 2b, questions 1, 3, 5 to 10 and 13. Please get in touch if you have any problems at all.